A very good morning to all of you. I cordially welcome you all for this engineering thermodynamics course. And today's classroom discussion topic is we have to prove that entropy is a property of a system, and we have to discuss about what do you mean by the entropy principle and what are the applications of the entropy. And what is the motivation to study these topics is it is very essential to know the principle of entropy and to know its applications in our day-to-day life. So I've already discussed about the objectives of the today's lecture, and the outcome is at the end of the class you should be able to analyze the applications of entropy principle and prove that entropy is a property of a system. And how can we prove the entropy is a property of a system? So just you go through the schematic diagram of the PV diagram of the entropy. And in the beginning classes, we studied that what do you mean by the point function and path function. So path function is nothing but whenever it is dependent on path followed by the system, then it can be said as path function. And the examples are work and heat. And point function means it is not at all dependent on path. That is, it is independent on path and it is dependent on only the initial states as well as the final states of the system. That is, here it is dependent on only initial state 1 and final state 2, and it is basically not dependent on whether it is a path A or path B or path C. Then it is known as the point function. And you know that all the point functions are thermodynamic properties. So that's why, so if you want to prove entropy is a property of a system, so first of all, we have to prove that entropy is a point function. So all the point functions are examples of the thermodynamic properties, and these are the exact and perfect differentials. So based on this particular the concept, now we are going ahead with the entropy is a property. So for this particular one, so here I have considered a cyclic process 1A B2. So let us say that this is my path A, this is my path A, and this is my path B. So I am considering is a 1 to 2. It is following according to the path A and it is coming back along the path B. So now whenever we are having 1A B2 cyclic process, that is the initial state is restored back along the different path. That's why it is known as the cyclic process. So in this particular the cyclic process, you can write down the entropy, that is the cyclic integral of the delta Q by T. That is the formula is nothing but ds is equivalent to delta Q by T. Since it is a cyclic process, so we are writing down the cyclic integral of the delta Q by T is equivalent to delta Q by T along the path A and delta Q by T according to path B. Now the path B is replaced by path C. So whenever it is replaced by the path C, now we are considering 1A2C1. That is 1A2. That is here you can consider here 1AC2. That is the 1A2C1. That is initial state is restored back according to the path C. So now the A is common in the previous case as well as in this particular case. So that's why delta Q by T according to the path A both are same. Now here the B is replaced by is a path C. So whenever we are subtracting this particular the equations, so we are able to say that delta Q by T according to the path C, it is equivalent to delta Q by T according to the path B. That is, so the delta Q by T value is saying if we take path C or path B. So that indicates that, so it is independent on path followed by the system. So whenever it is independent on the path followed by the system, automatically it says that it is an example of the point function. So point function means automatically delta Q by T. So it is not at all dependent on the path. So that's why we can say that it is a property. So ds is equivalent to delta Q by T. It is valid for the reversible process. So like this, we can prove that entropy is a property of a system. So that is always just you have to remember the important point is that, so based on the point function concept only, we are able to derive the entropy is a thermodynamic property. So that is very, very important point always we have to remember. So then we are going for the next outcome of our lecture, that is the entropy principle applications. So where you find the applications of the entropy principle, that is what entropy principle says, that is the ds of the universe is always greater than or equivalent to 0. So that is, for an irreversible process, the change in entropy of the universe always increases, it never decreases, it will remain constant for an irreversible process. So that is, the ds of the universe should be always greater than 0 for an irreversible process. So it should be equivalent to 0 for a reversible process, but it should not be lesser than 0. If it is lesser than 0, then it is violating the second law of thermodynamics. So now whatever the applications you take, our intention is to prove, that is the change in entropy of the universe always increases for an irreversible process. So with that intention only, we are taking some of the applications of the entropy principle. So this is the basic gist. So now with this intention, let us consider the first application, that is heat transfer through a finite temperature difference. Heat transfer through a finite temperature difference. Always you have to remember here finite. So finite temperature difference always leads to an irreversible process. Now the same thing we have to prove. So this particular application is leading to an irreversible process. So for this particular one, we have considered the two reservoirs. Reservoir A is maintained at a TA temperature, reservoir B is maintained at a TB temperature, and now here it is TA is greater than TB, so then only the heat transfer is possible from TA to TB. So that is higher temperature body to lower temperature body, so the heat is transferred according to this particular one. So now how can we write down the universe, that is the entropy of the universe is nothing but SA plus SB, because we are having the two reservoirs. So now ds of the universe is equivalent to dSA plus dSB. So now what do you mean by the ds universe? That is, how can you write down the dSA? That is, normally the formula is the dSA is nothing but delta Q by T, or simply here I have written the Q by TA. So this is the Q by TA. Why I have put here the negative sign? Why you have put the negative sign? That is, here the heat transfer from the system, that is heat is leaving from the body A. So in the initial chapters we studied about the sign conventions of the work transfer and heat transfer. So heat transfer to the system is always positive, heat transfer from the system is always negative. So based on this particular one here, I am keeping the negative sign, because always here you have to remember why I kept negative sign here, because heat is leaving from the system. So minus Q by, what is the temperature of the reservoir A? It is TA. Now the reservoir B, that is heat is transferred to the system. It is transferred to the body B or the reservoir B. So that's why here the heat transfer sign is positive one. So that's why here it is the plus. So plus Q by TB. So now here you are able to say that Q into TA minus TB by TATB. And initially I have already told you that TA is greater than TB. That's why only the heat is transferred from the higher temperature body to the lower temperature body. So automatically the delta S universe is greater than 0. So it is leading to an irreversible process. That is, it is satisfying the entropy principle. So that is, the ds inverse should be always greater than or equivalent to 0. So since it is greater than 0, now we can say that so heat transfer through a finite temperature difference is leading to an irreversible process. Now let us go to the second example, that is the mixing of two fluids. So that is, our intention is to, we have to prove that mixing of two fluids leads to an irreversible process. And for an irreversible process, we have to prove that ds of the universe should be greater than 0. So for that particular one, so we have taken here, it is the adiabatic container we have taken, that is, it is a hatched portion, it is representing is a adiabatic. So there is no heat transfer, that is the meaning of the adiabatic enclosure. So in between we are having one partition wall. So that is, we are separating these two gases by keeping a partition wall. So the subsystem 1 is having, that is the mass flow rate of the working fluid as M1, specific heat of the working fluid as the C1, temperature as the T1, and similarly the other working fluid which is there in the subsystem 2. So mass as M2, specific heat as C2, temperature of T2, and we are assuming that T1 is greater than T2. So with this particular condition, we have to prove that the mixing of two fluids is leading to an irreversible process. So since it is an isolated, so heat lost by the hot fluid should be equivalent to heat gained by the cold fluid, that is the energy balance. So now M1 CP1, because TF, it is a common temperature, it is the intermediate temperature after the energy balance. So T1 minus TF is equivalent to M2 CP2 into TF minus T2. Now here we can find out what is the intermediate temperature value like this. And now we can find out what is the ds of the fluid 1 and the ds of the fluid 2. So like this we are able to find out. So this is basically leading to the ds of the universe value is always greater than 0 because arithmetic mean is always greater than the geometric mean. So because of this particular one, we can say that, so the change in entropy of the universe is always greater than 0. It is leading to an irreversible process. So that's why we can say that mixing of the two fluids is leading to an irreversible process. Let us take the another example. So here we can find out maximum work obtainable from two finite bodies at different temperatures. Now here T1 is approaching the TF, that is the final temperature. So T2 is also approaching the final temperature. So this heat engine is operating between the T1 and the T2 and it is producing the work is equivalent to Q1 minus Q2. So write down the entropy of this particular the body 1, that is a delta Q by T. So mCp dt by dt. So per unit mass we are writing down. So Cp delta T by T. So Cp log Tf by T1 because T1 is the initial temperature and the Tf is the final temperature. And similarly you write down the entropy for the body 2 from the delta Q by T, but here initial temperature is the T2 and the final temperature is the TF. So from this we are able to have log TF square by T1 T2 is greater than or equivalent to 0. So that is log same thing, log TF square by T1 T2 is greater than 0. So from this particular one we are able to obtain the maximum work obtainable is always equivalent to Cp into square root of T1 minus square root of T2 whole square. So it is a very important derivation. That is, how can we find out the maximum work obtainable from a finite bodies which are operating with the T1 and T2 temperature limits. So already we know that the entropy change, how can we find out the entropy change of a system? That is nothing but the final state entropy minus initial state entropy. That is nothing but S2 minus S1. So isentropic process, how can we find out? Because isentropic process, I've already told you that is a reversible adiabatic process. For adiabatic process, delta Q is equivalent to 0. So delta S isentropic will becomes S2 minus S1 is equivalent to 0. So S1 is equivalent to S2. That's why it is called as a reversible adiabatic process and it is also known as isentropic process. The same thing here I have represented. So now it is simulating a reversible process. That is, how can we obtain a reversible process in the actual practice? Now, I have already explained you one of the example whenever we are discussing about the quasi-static process. That is, whenever we kept some amount of the weight on the piston. So that is, instead of keeping 1 kg of the weight, so we kept some 10 grams of the weight into 100 in the number. So whenever we are removing the 10 grams of the weight, so the deviation from the equilibrium states is very infinitely small. So we can assume that that particular the process is leading to a reversible process. The same thing in the similar manner we can have the another example here. So here a sample of the gas is confined in a volume of 1 liter by the pressure of a beaker. So whenever just you are removing only one sand grain, another sand grain, another sand grain, so that is the deviation from the equilibrium states is very infinitely small. So like that we can simulate this particular example as a reversible process. So like this we can study, that is the entropy principle. So entropy principles are a very important one, and already we have proven that entropy is a property. I hope you understood the concept of the entropy principle and its application and property of entropy. Thank you one and all for listening this particular lecture, and we will meet you once again in the next classroom discussion topic. Thank you.